Let me first talk about the paper. Somebody reminded me that I hadn't talked about it. Oh yeah. It's gonna be super simple. I'm just expecting you to read and understand academic literature, right? Not come up with anything original or anything like that. Find one paper on algorithms that interests you. Read it. Then every academic paper has a bunch of references at the end, right? Has a bibliography at the end. Find two of those in the bibliography and read it, and that gives you kind of an overview of whatever topic. And then I'm expecting about a paragraph summary of each paper. You can paraphrase the abstract. Each paper will have an abstract, right? But I really want to see your take. What I'm interested in is, did you read it? Did you think about it, right? So I would much rather see your take on it. So I'm expecting something like a paragraph summary of each paper. And then a 2-page reflection of probably all three of them, right? How does it relate to the material that we covered? Is it important? Why do you care? Those kinds of things. Does that make sense? And the more specific and the more tying it to the material, the better, right? Like, yes, it uses a greedy technique here, and this other guy proved that greedy is optimal for this problem, or the other way around, they proved that greedy is not optimal, so they use dynamic programming, and it's order of whatever, right? And that's it. Well, and a 5-minute-ish presentation.
That include PowerPoint slides and everything, or you just want us to stand up?
I don't know about you, but yes. Normally it's a lot easier to stand up with PowerPoint slides, right? I'm not expecting, I don't give a hoot about, I don't terribly mind about presentation of the presentation.
Okay.
Right? Bullet points, right? Whether you put them in a PowerPoint and whether your PowerPoint has 17 transitions and animations and things like that, I don't terribly care. And then what we will probably do is we could do a presentation day or two, or we could do online. You record yourself with screen. What do you prefer? Class?
Can we have one meeting?
Online.
Sorry?
Can we have a week to
We just throw out the presentation part.
We'll
I mean, you already had guys writing 2-page paper.
Week 2 days be enough for everyone.
Reflection time.
that's what. How about we do it voluntary? You can either present it in front of the classroom or record a 5-minute thing.
Okay, whenever you do recording, you need audience or just
No, just kind of what we have been doing, right? A screencast or something like that, or record yourself with a camera, whatever makes you happy.
Are those consolidated in one, at least 3-page paper, or are they 2 different papers?
I'm assuming that I'm one 3-page
Okay.
paper. I don't. If you submit 2 files, I'm not gonna.
Not to hash on specifics, but it does change how long the paper is. Do you have any spacing requirements?
Sensible stuff.
Okay, yeah, so nothing crazy. but-
64 font.
Here's the deal. Here's the deal. If you notice, I actually put squiggle lines next to all of those things, right? Because I want you to put all there is to say, but no more, right? So if you end up with a page and a half, and you actually read the paper, right? You look at it, the stuff, right? And there's only a page and a half of stuff to say, that's perfectly okay. Don't go making it 14 points bold, double spaced, right? There is no point in doing that. On the other hand, if you find out that there is 3 or 4 pages of stuff to say, that's okay. Now, if you find that you only have 3 lines of stuff to say, that's too little. If you find that you're doing 20 pages, that's too much, right? I mean, I'm not gonna weigh these things. I'm probably gonna read them. I'm gonna read them. I'm gonna, if each one of you give me a 20-page paper, I'm gonna sit and cry. Because there is more of you than me. So, don't, right? I'm expecting, and what I really want to see is that you read and understood and thought about it. On the other hand, I do expect above high school level presentation, right? I expect this to be typed. I expect that if you use math symbols, you actually put math symbols. And I expect that if you're going to put a diagram or something like that, you put a diagram or a graph that actually makes sense, right? And it's done with computer tools. We are all computer people here, right? I expect something better than my 12-year-old could produce. On the other hand, I don't expect you to spend 2 days trying to make it pretty and figuring out which shade of blue goes better or something like that. Do you get the idea? Yes. Any questions about this stuff? No. Where do you find papers? I'm actually giving you a link to this. To me, this is the first place that I come to. I don't know exactly what is the deal with Kennesaw. I know that within the school, you can access it and download full text pages, full text papers. I have no clue how you can access it from home. There is probably a VPN or something like that. If you go to the library page, they'll probably tell you somewhere. Yes.
How specifically related does it have to be to algorithms? Like, does it have to be a paper specifically about an algorithm, or can it be a paper that just describes an implementation of something, and then we tie it back in our reflection? Like, if you already have a paper in mind.
Ask me with a paper in mind, rather, right? As long as it makes sense. But if it's a paper, it's a computer graphics paper that happens to tangentially mention that they use the Bressingham algorithm, then that's not it, right? As opposed to a paper that mentions algorithms in a particular context or something like that, right? And hopefully this will actually push you to be slightly more familiar with that stuff and kind of go find something that interests you, right? Any other questions? When is it due? A week? No. Here's the deal. Let me do this. Let me push you. I will create. Actually, no. Let me actually not lie to you. Let me go create a discussion list, right? A forum. I'm gonna ask you to maybe. What, didn't I create that stuff?
Yeah, it goes there.
Ah, never mind. I cannot read. What is reasonable? 10 days for you to post here. So by next Wednesday, today's Monday. Is that reasonable? Go find a paper, right? Go find something that interests you. Is that reasonable?
What will be the subject?
Sorry?
What will be the subject for the paper?
You have to read a paper on algorithms and then follow 2 of his references.
On Android.
Yes. Any. It has to be a research paper and it has to be about some topic related to algorithms or data structures. You could go find a really fancy data structure if that makes you happier. Does that make sense? Is that reasonable? Yes.
So what do you want? You want us to post our links, the paper we're going to use?
Yes.
Next week, Wednesday?
Yes.
Okay.
And then probably by that's the 19th. November 16th, 4 more weeks. You're done. Is that reasonable?
We have to write a discussion from the paper.
Yes. Sorry, I think you walked in late. Yeah, we went over all that. It is recorded. Yes? And that's not too close to the final, so you don't have everything else due. Reasonable?
What will be the presentation?
Some in the weeks after. Well, either the 20th or the 23rd or something like that, depending on how many people want to volunteer to present rather than record. Make sense? Let me go. Has due date 11/16. Yeah. Yes. Beautiful. Makes sense? You're all cool? So good. Yay! Any other questions? Do you have to get it from here? No, as long as it's an academic paper, not a blog post, not a, right? Cool. Then let's finish talking about dynamic programming. Reminder, what's the idea of dynamic programming? What's the main thing about dynamic programming? What are we doing?
We're breaking it into sub-problems so we can repeatedly solve that.
We are breaking it into sub-problems, right? Just like in divide and conquer. What's the main difference? You do recursively in divide and conquer too, right? What's the difference between dynamic programming and divide and conquer?
You save those sub-problems up so you don't have to recalculate them several times.
Yeah, you would end up overlapping sub-problems, right? You would need to solve each one of those sub-problems a bunch of times if you were to doing naively, so you store them all, right? Which may be what you were trying to say. But so we did see a couple of other ones. Let me actually. We did talk about weighted inverse scheduling, segmented least squares, one version of the knapsack problem, and RNA secondary structure. So this next one is similar to the RNA secondary structure. It is sequence alignment. How similar are two strings? Imagine that you're trying to compare occurrence and occurrence, right? And if you notice, one of them has only one C. Have you seen this kind of stuff? No. Oh, standard problem is when you mistype something, right? So how can we specify, are those similar? Are they probably a typo, or are they two completely separate words? Right? What can you do? Do you remember with RNA we were talking about pairings, right? You pair letter number X of this one with letter number Y of this one, right? This is very similar idea, right? You're gonna try to match, right? And what happens on the first one? You could have we would match basically every letter as they come. So we'll match the O's, we'll match the C's, and then we have two that don't match, then one more match, right? And a bunch more mismatches, right? So we'll have 6 mismatches and one gap at the end, right? One letter on one place that is not matched, because they have different lengths. We could do a lot better. We could put the gap on the third letter-ish. Well, there is no letter there. We'll put a gap after the second letter of the first word, right? So we'll match the O and the C, then we'll skip on occurrence that only has one C, and then we'll start matching again, and the letters match, right? The U's match, the R's match, then we have a mismatch, an A versus an E, and then the other 3 letters match, right? We could also do it like this. At the bottom, we would just skip, and so we'd have 0 mismatches and then 3 gaps. Which one is a better match?
Depends on how you weight mismatch and gap.
Yeah. Which one really sucks?
First.
First one, right? Second and third, right? Depends on mismatch versus gap. Does that make sense? Many times we also, for something like English, it probably makes a lot of sense to say there is different letters. There is a degree of mismatch between the mismatches. English is horrible with vowels, right? Which means that native English speakers will just put any vowel in the middle because it doesn't make any difference. You can just put whichever vowel you feel like it, and the word would probably sound the same, right? It's not quite true, but as you can see, I'm not a native English speaker. Feels like that sometimes, right? I think we probably have more non-native English speakers than native English speakers. So you all understand me. And so vowel mismatches are probably not as important, right? Probably. Maybe. I have no clue. Consonant mismatches are probably more important, and then some particular letters may be more important or less important, right? So we could have the mismatch penalty would actually vary between letters, right? And so Levenstein is one of the first guys who talked about that stuff, and actually the algorithm will do. I used to know it as Levenstein's algorithm. There is a gap penalty, something that we do per gap, and then a mismatch penalty that varies by the combination of letters, right? So maybe A and E are not that dissimilar in English. A and F are probably very dissimilar, right? Simplification, you could just say, well, if they're different, they're different. If not, you can say, well, these two are very similar or not. Where do we use this, right? We actually use it for stuff like spell checking and things like that. In Unix, the diff algorithm is basically this, comparing whether something changed in a file. And so it will show you the lines that changed in Git and that kind of stuff. That's this diffing algorithm. For speech recognition, you have the same thing. You have these phonemes. They're trying to mention something. And then it is actually probably now a lot more useful in computational biology. One of the really cool things, when you look at DNA, right, and RNA, which we talked about a little bit last class, biology is just strings. And then actually your DNA or RNA encodes proteins, so you can see them as strings of proteins instead of strings of genes, but it's still strings. Isn't that cool? And there is tons of interesting stuff with that. So what's going to be our problem? Given two strings, x1 to xm and y1 to yn, find a minimum cost alignment. And an alignment is a set of ordered pairs xi, yj, such that each item occurs in at most one pair, and we have no crossings. Actually, some other formulations have crossings for transposing, which is a common thing when you're doing letters. Right? You just put them in the wrong order. And that would be a crossing, but in this formulation, there are no crossings. The cost of an alignment is going to be the summation of the cost of mismatch plus the gaps, right? You can think of a gap as an element in one that is not matched. So the sum of the unmatched in x and the sum of the unmatched in y times some constant. These constants are important. However, they are not important for the algorithm. So when you go apply it, it is very important. Am I doing gene comparisons? Am I doing proteins? Maybe proteins are very similar to each other, and so it's not as important which proteins. So what you're doing may actually be important. As far as the algorithm is concerned, these are inputs to the algorithm. Does that make sense? Now, we are going to define as OPTIJ is going to be the minimum cost of aligning prefix strings x1 through xi and y1 through yj. Right? So I and j are the character on both of those. Our goal is OPT of m and n. And basically, if you think about it, if you're matching toward at the end, you either match the last two letters or one of them will be a gap, right? So this is the same thing. So when I have OPT of ij, I either leave, I either match I and j, so that would get, that the cost would be the mismatch for xi and yj, plus the minimum cost of aligning from x1 to xi minus 1 and y1 to yj minus 1. Right? I match those two letters, so it's the minimum cost of aligning the previous string. I could also leave xi unmatched, and so I will get the gap for xi plus the minimum cost of aligning x1 through xi minus 1 and y1 through yj. Right? I didn't match xi, so now I go xi minus 1. Or I could leave yj unmatched, and so I will have the gap on, I'll get to yj minus 1, right? And I have two base cases just in case, which is when I is 0, then I have nothing to match. So I would just have j times delta, or j is 0, then I'll have I times delta, right? And then that is the definition of OPT of ij. If you notice, I have tons of overlapping subproblems, right? So what do? Create a table, right? How big is my table? What does it contain? N squared, what's n?
Column and row.
The longest string?
Length of
Length of string, are they the same length?
No.
So
Depends, yeah.
is what? M times n, right? Or something like that.
Yeah.
Right?
Do the gaps that you possibly put in one of the strings count in the table? Or-
Not really.
Okay.
They will not make your table any bigger. Yeah, no, because you're going through up to character I or j in your string, so no. So we could do it like this, right? Just initialize here, and then go inside and calculate the minimum, right? And then how do I calculate my sequence? I could either actually keep track in there of what did I do, or come back and do it from that thing. I would normally keep track of it, because if not, I would get lost if I was implementing it. But how bad is this in terms of time and space, right? It takes order of m times n time, right? I have my nested loop, and it takes order of m times n space. Does that make sense? That's basically the size of my matrix. Does it suck? Maybe. We can cheat a little or a lot in space. In terms of time, we're doomed. That's what we have to do. In terms of space, we can cheat somewhat. First of all, if we only care about the size, about the cost, then we can actually kind of delete the stuff that we are not going to use from the table. So we really only need 2 rows, the one that I'm computing and the previous one. So that would give me O of m of n time and O of m plus n space, but it makes it a pain to recover the optimal alignment. So you could just store it, but there is a prettier, cleverer algorithm for using O of m plus n space. You could think of these edits as a path on the edit distance graph, where each one of the moves, right, would take you, and these are the costs, right? If you think about Fij is the shortest path, right? In your graph, you can move by either matching or gapping, right? So this is matching, right? Matching is a diagonal move, and gapping on X or on Y are vertical or horizontal lines. And eventually you need to reach to Mn. So this is just, you could think of this as kind of distance, right, on this graph, go from 0, 0 to Mn. So we can prove that Fij, which is the distance, is OPTIJ. And so we can compute f of whatever j, right, in order of m of n time and order of m plus n space. And so we can cheat if we have the shortest path. We can also compare the reverse, the one from Mn, or from Ij to Mn. And so it does a horrible thing that uses divide and conquer and this stuff. To be able to calculate um, the optimal alignment with a lot less space. Why is that important? It's actually longer runtime, right? But you don't need as much space. If your sequence is DNA, then your strings are 1,000,000 by 1,000,000 or something like that. So it does increase the running time, or at least increases the constants, but saves you space. Chances are that I would figure out how to put more RAM on my friggin' machine, but you do need to know this exists. You don't need to really know it. Another cool algorithm is the Bellman-Ford algorithm. Is shortest path. Did we see a shortest path algorithm before? Whose algorithm it was? Just put a bunch of names, right? Who? Prim? No, Prim was Dijkstra or Dijkstra, or I have no clue how it's pronounced. It's Swedish or something like that. I have no clue. I'll pronounce it Dijkstra. You guys can find out the right pronunciation and correct me. It's probably wrong, but I don't care. That algorithm works if your edges are all positive, right? Or at least non-negative. It doesn't work if you have negative edges. Do negative edges make sense? Maybe. What's your problem, right? For many problems, they don't, and then we have super easy, and we can use Dijkstra, right? Which was greedy and was fast. For some of them, you have negative edges. And this could be, right, one of the things they talk about is arbitrage. So this could be transforming coins into from one coin to another, from like dollars to pesos or to pounds or to euros. And sometimes you can actually make money by doing that, right? And this could be actually many times you have weird things where they pay you for doing stuff, right? The electric company may actually pay you to use electricity at some point in time because they have too much and they don't want to stop their turbines or something like that, and they have to do something with it. So depending on what is going on, right, you may actually have negative things. If you do, then Dijkstra doesn't work anymore. So, what do you do? Cry.
I had a question
Yes.
before we moved on. So what's stopping you from just adding a constant to everything?
Yeah, good question. Smart guy. Does it work? Let's see. That's the second one, right? Let's assume that my lowest weight is -10, right? Just add 10 to everyone, right? And so now it would work with Dijkstra. Does it give me the same path? Maybe not, because now if I have a path that has 3 nodes versus a path that has 2 nodes, the path that has 3 nodes I added 30. The path that has 2 nodes I only added 20. So it's not guaranteed to give me the second path. That is the reweighting idea. Very good that you came up with it. Still doesn't work, but right? It's good that you're thinking. So we can't do that. Um, we need to start thinking about other stuff. One idea is a negative cycle. Negative cycle is a directed cycle such that the sum of its edge weights is negative. What happens if you have a negative cycle? What's the shortest path?
That cycle,
Not just that cycle. How many times do you take that cycle?
as many times as possible.
An infinite number of times, right? So there's really not the shortest path anymore, right? Just keep doing it forever. And chances are that your actual problem doesn't really have a keep doing it forever. So our lemma one is if a path from B to T contains a negative cycle, there is no cheapest path from B to T because we could just go over that cycle over and over, right? Now, if G has no negative cycles, then there is a cheapest path. It is simple, that is, it doesn't have cycles, and it has at most n minus 1 edges, right? Because it's simple, so it can never have the same vertex more than once. Because, well, if we had a cycle, since we know that it's not negative, we can just take it out, right? In a way, these are very related problems. One is single destination shortest path problem. So given a digraph G equals VE with edge weights CVW and non-negative cycles and a distinguished node T, find the cheapest path from V to T for each node V. And negative cycle, given the digraph, can you find a negative cycle? So, what can we do for dynamic programming? OPT-IV is the cost of shortest V to T path that uses less edges less than or equal to I. Let's see. Sorry. So we have two cases. We either use less than or equal to I minus 1 edges, in which case we are going to get the same cheapest path, right? From OPT of I minus 1V. Or we are going to use exactly I edges. So we are going to add a BW edge and then select the best path from W to T using less than or equal to I minus 1 edges. So my formula is either infinity if I equals 0, I cannot use any edges at all, or the minimum of OPT I minus 1V, or the minimum for every edge VW of OPT I minus 1W plus CVW. Right?
Can you give a little bit deeper explanation into what each of those are? Like, I got it all the way up until that.
Okay, basically, let's go try to draw stuff as usual. See. Let's see if we can. So let's say that we have, from A I can go to B, or to C, am I making any sense? So my first is taking 0 edges. I can, right? Let's assume that I'm trying to do to D. Taking 0 edges, can I do anything? No, right? Well, what's gonna be my final thing? There is 1, 2, 3, 4 vertices, right? So my final thing is gonna be taking at most 3 edges, right? So my final thing is gonna be to D on 3, right? So I have 2 choices. Either however many, right? Either whatever is the best path for 2, or going to C on 2 and then taking the edge from C to D. Does that make sense? That is this stuff.
Okay.
That makes more sense. Without throwing stuff on the board. That's not recordable. And so if I had more edges that take me to D, right? If I had from B to D, say by 4, I could have, or let's do this. Right? Now it would be, well, I can either go to C, right, and add 3, or I can go to B and subtract 2. And that may be more attractive, right? But now I only have 2 edges. I cannot use 3 anymore, right? Because my path is going to be at most n minus 1 edges.
Okay.
And so I need to go through every edge that ends in W. In our case, it was D, and calculate that stuff. So I could, the bottom up is start 0v is infinity for cost, and 0 to t, which is where we want, is 0. That's just to get it started. And then I'm going to go for I equals 1 to n minus 1, go through each node, and start with this one. MIV is m of I minus 1v, and then go through all the edges and check, well, would this one be smaller at the second place, then I will replace MIV with that number, right? So MIV is the minimum of whatever it was, MIV plus the other possibility, n minus 1w plus cw. And eventually, I fill up my table, and I get that. Does it make sense? No, maybe. How long does it take? takes order of mn time and order of n squared space, right? Where m is the number of edges, because in here I need to go check every edge, right? How do I find the actual shortest path? I can actually keep track of it, which maintaining a successor table, or do it again and kind of go figure out which one did I use. We can optimize a little bit by keep track of the cheapest path that we have found so far. Since we are going to go from I equals 0 to I minus 1, right? We are never, once we get the one with 3 edges, we are never going to look at the one with 2 edges anymore, right? So we can just keep one, the best one we have found so far. And keep the successor. And there is another trick, which is if we didn't update the cost of a node during one iteration, then there is no reason to consider that node in the next iteration, because it's not gonna produce any new values, right? So with that, we can do it now rather than we can do it like this, and we can actually short circuit our algorithm by, if we didn't change anything, even though we should look at n and I equals 7 and 8 and 9, nothing changed, so I know that I'm not going to find anything better. So depending on what you are doing, this may be, it's probably better. It's better in space. It may be better in time. May actually be slightly more complicated for no gain in time. But does this make sense? A similar thing is distance vector protocols. How do you keep track of networks, right? If you think about it, networks, right? Computer networks are basically these graphs and cost and things like that, right? As we talked. If you think about it, the node is the router or switch. Well, yeah, router. Sorry. The edge is a direct communication link, and the cost of the edge is your delay on the link or an actual cost if you're trying to minimize cost. Most of the time, there is no money changing hands. Sometimes there is. You could apply something like Dijkstra's algorithm, but it requires information of the whole network. You could apply something like Bellman-Ford, and you only need the knowledge of the neighboring node, which makes it better. It happens to be that you don't need to worry about synchronization. These algorithms will converge. There are distance vector protocols, routing by rumor, right? They tell each other how the next hop is going. each router maintains a vector of shortest path length to every other node, just the length, not the path, and then the first hop of the path, and then I don't care, right? I just send it to that router and it's their problem, not mine. And so when it gets to what do, I just go figure out which one will take me there faster and send it to that point, right? Some of the things did that stuff. I don't think we use any of those things anymore. Maybe Cisco's, but I don't think everybody uses BGP, except for those who don't. BGP is kind of the most common one used. Each router stores the entire path. It's based on dice trace. Dice trace avoids counting to infinity problem. So it is slightly more complicated, requires a lot more storage, but this is another application in a slightly different context of these kinds of algorithms. How can I find negative cycles? One possibility where this would be important, right? For routing on the network, you tend to not have negatives, but actually, yeah, maybe. There is arbitrage, right? Imagine that you have currency conversion, right? What happens if I go to the airport with $100, change it into euros, and then change it back into dollars? What's probably going to happen? I lose money. Why? Service charge, right? And if you go to the airport, they are outrageous. If you're a bank or something like that, then you can do it for tiny service charges. But still, you normally find, right? There is usually a tiny service charge, right? However, once you have, right, a bunch of currencies, it may be that I can, as a bank, get dollars, make them into euros, then Mexican pesos, then Chinese yuan, yeah? Yuan, and then back into dollars, and I actually end up with more dollars, right? Because of the differentials, right? So could I find arbitrage, right? And if I do that, what do? I do it quickly and then do it again and then do it again until those rates change and then I cannot make money anymore, right? So that would be an example where negative cycles are very, very good. Now, if we are doing the Bellman-Ford algorithm, if OPT of NV is OPT n minus 1V for all V, then no negative cycle can reach that T. However, if OPT NV is less than that OPT n minus 1V, right? So there is at least one where having a longest path is going to get me smaller, right? Smaller cost. Then any cheapest path from V to T will contain that cycle, and that cycle will be negative. So I can basically do a modification of the Bellman-Ford algorithm and detect a negative cycle. I can actually make it, I connect every node, add a new node, connect all nodes to T with a zero cost H. If OPT of NV is OPT n minus 1V for all the nodes V, then there is no negative cycles. If not, I will find that negative cycle from that extra node, right? Because I don't know where the cycle is gonna end. And it could do other stuff, weird stuff, for this to not do order of n space if it's important. Any questions? Life is good. You know all there is to know about dynamic programming. I will, politicians promise, I will pose problems like I did with assignment 3 for some of this stuff. I'll probably do one for DP and network flow. We'll do network flow next class. Now I'll give you back 10 minutes of your life, unless you have questions.